concerned, it's fine. Yeah, all the students, please, if you can see the slides.
Yes, sir.
Yes, sir.
Yes.
Okay.
Yes, sir.
Can you hear me properly also?
Yep. Yes.
Yes, sir.
Yes, sir.
Okay. Okay.
Yes,
Nice.
okay.
Okay. So, Assalamu alaikum to all of you. And it's as I said, it's a great opportunity that I've been invited by respected Dr. Mubashir to deliver a lecture on a very important topic in geotechnical engineering. In fact, this is the most important topic, at least as far as my belief is concerned, in geotechnical engineering, and the least understood and least used, at least I can say, least used area by the geotechnical engineers. That is constitutive modeling. So during the course of this lecture, you will discover the importance of such type of modeling for soils, and its importance in not only in geotechnical engineering but in civil engineering in general also. Okay, I'm not sure about the general background of all of you, but Dr. Mubashir ensured me that you people have enough knowledge that you people can well understand the steps or the sequence that I will be following in delivering this constitutive modeling lecture. So to start with, what should be my lecture outline? As any typical introductory lecture, as typical of any introductory lecture, I would be answering all the questions that should be in the mind of a listener. First of all, like, what is constitutive modeling? Why we go for such kind of modeling? Where we use it and how we use it, or how we come up with the modeling. So all these kind of questions I'll be answering. So that's the outline of today's lecture. During the course of the lecture, I would welcome any small questions or clarifications so that the continuity of understanding should be there. But general discussions or general questions, I think it's better we will have, inshallah, by the end of the lecture. Okay, so what is constitutive modeling? First of all, I'll go with the general definition, and then I'll come back to the specific definition for soils, or the specific definition which we usually use in the field of soil mechanics or geotechnical engineering. Now, the general definition of constitutive modeling. It's just to make it very easy, in physics or engineering, a mathematical model that describes the behavior of a material. Okay, I'll just take the laser pointer. So a mathematical model is the most important thing, and that describes the behavior of a material. So first of all, we have to understand the behavior of a material. We have to translate into its mechanical form, and finally into a mathematical model. So that's what is constitutive modeling. But in very general terms, when we say constitutive modeling of materials, then it's a response of a material to the external stimuli or fields. So it's a very, very wide definition, and it's not only applicable to like civil engineering materials, but it's applicable to all kind of materials that we can even imagine. Now, there are two aspects of this definition. One is the response of a material to external stimuli or fields. Or let's take, first of all, what is an external stimulus or field? Okay. So what usually we have as external stimulus or field, as far as we as civil engineer knows, that we have two possibilities of an external stimuli. One is stress, which is very common understanding, but another one is environment also. So environmental loading is a very common definition now these days being used by the geotechnical engineers, like change in moisture content, change in type of fluids in the soil, change in the level of contamination in the voids present in the soil. So all these external stimuli like stress or environment fall under that one. But in addition to these stimuli, we could have other stimuli for other kind of materials or other kind of materials present in other fields, other engineering fields or scientific fields. Like for example, we can have a magnetic field. If we place a material in a magnetic field, so we have to determine it's a response to a magnetic field, then it's also a constitutive model. If we place a material in a thermal field, it's again the study of the behavior. And finally, formulation of a mathematical model is again a constitutive model. Or even in an electric field. So we place a material in the electric field and we determine its behavior. So the final objective of constitutive modeling is to determine the behavior of the model in a mathematical form to any external stimulus or field present around it. So this is a very general definition, and then response is of course varies again. For engineering materials or materials generally we deal in physics, we say strain is its response, the change in the shape of the material, you can say. So whether it's a compressive strain or a tensile strain or a shear strain, or even a combination of all these kind of strains. But again, for all other general materials, we can have different kind of response. We can have change in the electrical properties of the material, we can have change in the magnetic properties of the materials, and so on. So in this one, in this slide, I have introduced you a very big picture of the constitutive modeling, which is applicable to any kind of material in engineering or science fields. But now I would like to come back to the definition that is applicable for the soils. So in soil mechanics or in geotechnical engineering, the definition which we use is the relation between the stresses imposed and the resulting deformation at a macroscopic level. Now, all these terms are very important to understand. So that we have stresses imposed. It could be either internal stresses or it could be external stresses, or the stresses due to loads or stresses due to the environment, as I mentioned to you. So change in water content, change in water table position, or any other such kind of phenomenon could result in deformation of the material, but it should be at the macroscopic level in general. Okay. The constitutive modeling concept which I'm starting with is applicable to a continuous material. So we called it continuum in general terms. So and the branch of mechanics that deals with it, we called it continuum mechanics. So for the time being, you have to assume that this material is a continuous material, and the behavior is applicable. Behavior of the material is visible only on the surface. So deformation is there. Okay. So all the internal strains and the change in the dimensions of the material or the shape of the material should be visible at that one. So mathematical relationship that exists between these stresses and the deformation at the macroscopic level is known as a constitutive model in the field of soil mechanics. I just want to emphasize again the value of constitutive modeling over here, although I mean I have said it to some extent in the beginning, but it's important to say that usually as geotechnical engineers we are dealing with the empirical methodologies. We are dealing with the closed form solutions. So for such empirical methodologies and empirical solutions, we come up with the bearing capacity and deformations or the settlements of foundations and other structures founded on the soils. But if a person is restricted to this level, usually we call it a foundation engineering. Okay, or he's dealing or he's practicing the foundation engineering. So it's very important to understand that if until and unless the constitutive modeling is involved in the practice, in the geotechnical practice, we cannot call ourselves as geotechnical engineers. So that's why it's very important to understand. And why I told you at this point, because I will be keep on showing you the importance and emphasizing it further and further during my lecture. So these are the two definitions over here. Now, one very important aspect I just want to make it further clear. So these are the definitions from physical point of view. So what's happening? Why we call it constitutive modeling? Now it is time to tell you about that one. Now, in any constitutive model, the most important aspect is the constituents of the material, or the composition of the material. Okay, why I put constitute? Because this stems, a constitutive stems from this word constitutes. So constitute of the material is very important. Generally, you know, there are many laws. Whenever we are doing modeling, there are several other laws that are applicable during the modeling. Okay, it's not only the constitutive model. Constitutive model only makes one part of the complete modeling set. But why it is important? Because it is highly specific for a material, because it depends on the constituents of the material, how the constituents make up that material, how these are distributed in a material, and how they interact with each other in a material. Okay, so that's very important to understand. Now, if we so general behavior of a continuous body, which is continuum, as I told you, is governed by many laws. Okay, many other laws, irrespective of the material of the continuum. Now, there are several other laws which hold good. Once I will list it, I think you people can easily recognize and recall these laws. And one of them is the law of conservation of mass, law of conservation of momentum, law of conservation of energy, and laws of thermodynamics. So all these laws hold good irrespective of the material content of the material, okay, or the constituent content of the material. So that's very important to understand again, that it's not only the constitutive law that controls the overall behavior. There are other laws, but those are not dependent on the type of the material, the distribution of the material, and the interaction of different kind of materials present in any substance. So that's why we call these laws or rules as constitutive laws or constitutive rules. Okay, so unique behavior of the material, that is the most important thing. So it's very, very important to understand. And you can see here that that's why we call it constitutive equations or laws or models, because these are applicable to the specific constituents. Now look at one of the example which I have just tried to sketch over here. You can see here there are two bricks, one made of concrete and one made of rubber. Now if I apply same load on both of them, what will happen? You can see here that concrete will deform little only, but rubber will deform too much. You can see here. Okay, so what is happening? All other laws are same for these two bricks: the law of conservation of mass, momentum, energy, and other thermodynamics. Even the configuration of both the material is same. But you can see here there is more deformation in rubber as compared to concrete. So this is what is the constitutive response. The response from the material of the object or substance or any general structure. So that's why when we say that it is highly unique to the material, so you can see here a general form of, at the bottom of the slide, you can see the general form of stress strain plots for different kind of materials. Like for example, the first one is glass and chalk. Okay, the second one is for steel. Then we have aluminum alloys. We can have this one applicable for the concrete, and finally the soft rubber. Okay, which I have shown you as one of the example over here. So always you have to keep in mind that the unique constituents of the material define the unique behavior of the material if all the other laws remain the same. Okay, so this aspect is very important. So whenever we impose a stress field on a material, there is an internal response, and it is related with or directly related with the type of the constituent of the material, the distribution of this material, and the interaction of material among each other. In geotechnical terminology, we use one single terminology for all these things. We call it structure of the soil. Okay, I'm not sure if you people have heard this terminology before or not, but it's very common. So we called it structure of the soil. I can give you more example to make you better understand. Like, for example, you have sand, and the particles are distributed in a dense form, or particles are distributed in a loose form, and there is a cementation present or there is no cementation present. All these properties together make or qualify the structure of the sand. Okay, so the behavior which originates from the structure of the soil is known as the constitutive behavior. I hope the definition or what should be clear to you. Just to give you a little bit more vision on what does it mean in the physical form, I have a couple of slides just to give you more idea. Like, imagine this is a continuous body. This is a continuous body, and we apply forces on it. So when we apply external forces on a body, there are two basically the reactions comes from the two aspects of this body. We called it physical principles and the constitutive behavior. Okay, so physical principles remain same for irrespective of the type of material, but constitutive behavior is related with the type of material or the structure of the material. I will start using the terminology structure from now onwards. And finally, which is not the intent of this presentation, is basically we go for the solution procedure. Okay, which is basically the converting or translating the mathematical equation, relation, or formulation into the computer language or into digital language. This is a solution procedure, and finally we measure the response. So for this lecture, I'll be just limiting myself to the constitutive behavior. Okay, another form just to show you how there is where does constitutive relation holds with respect to the other physical laws. You can see here, you people must have heard of the equilibrium equations, which is the relationships or the equations between force and stresses, and then you have strain displacement relation. We call it compatibility equations between displacement and strains, and then finally we have the relationship between stress and strain as the constitutive relation. Okay, so from here now I'll be starting with the simplest form of, just to give you an example, the simplest form of constitutive model that all of you must, as a civil engineers, must be aware of. Okay, that is the Hooke's law. Okay, this is the most simple type of constitutive model. So I just want you to start your understanding from this simplest form of the constitutive model, which is Hooke's law. And Hooke's law is nothing else but says that strain is directly proportional to stress, and there is a material constant which is E. It's called elastic modulus. So it's a direct relation. There is a direct relationship between strain and stress. And once in Hooke's law, once you unload the material, it comes back to its original position. So irrespective of the number of times you just make a stretch of the material, it will have a zero permanent settlement in it. So this is the simplest form of the constitutive law. Okay, and I'm sure all of you must be well aware of it. But you know, in any material, generally when we look at these plots, it seems that there is one dimension relationship. But no, in any material, which is basically a 3D material, we have different stresses that act in different directions. Okay, from I think material courses, mechanics of material courses, or strength of material courses, you people should have a good idea that we have three principal stresses: sigma 1, sigma 2, sigma 3. So if we consider all these stresses in the relationship, so then we'll have three different strains acting in three different directions, but still we call it Hooke's law. We call it a generalized Hooke's law. And now you can see here that there is a strain, there is stress, and you can see that in addition to E, there is another constant. We call it nu, or anyone who can tell me what is this? Are you still with me?
Poisson ratio.
Yeah, Poisson's ratio. That's good. Okay, so these two are known as material constants. Okay, so now these two are the material specific. Now, if we take sand, we'll have a different E, we'll have different Poisson's ratio, and if we have clay, we will have different E and different Poisson's ratio, and it depends on so many conditions or so many forms of clays, like soft clays, medium stiff clays, hard clays, dense sands, very dense sands. So both of these material constants again would be highly specific to the type of material. So this is the simplest form of constitutive model, and sometimes I have seen geotechnical engineers just rely on this one and they say, okay, this is enough. Or maybe more precisely, if I say more precisely, maybe structural engineers, they just consider soils as perfectly elastic material. They take it as Hooke's law, use Hooke's law to represent the soils, and there where they are doing a big mistake always. So we have to, first of all, we have to understand these things, and we have to come out of this small dilemma, or it's a small cover, and we should understand what is the importance of the constitutive modeling, and then we should go for better soil structure interaction models to get the most precise results. Okay, now this is the simplest form, and usually as civil engineers we are very well aware of a material. I think I'm not sure whether we are aware of any other material than steel. Okay, when we look at the constitutive law for the steel, you can see here, this is the plot. This is the plot, and you can see here Hooke's law is applicable only up to this part of the material. How about the other part? If we have to model this part, and definitely it is required to model in many instances, it is required to model this part of the behavior, then it will become a very complex constitutive law. Okay, and what is now special in it is the introduction of plasticity. Okay, plasticity is a behavior in which the material, when we unload the material, there is always a permanent settlement or a permanent deformation in the material. So the range of stress and strain where we have permanent settlements, we call it plasticity range. Okay, another name for this one is strain hardening range. Okay, so this definition might be new for you people, but at least you people should have an idea about the plasticity. Okay, so then you get an ultimate strength, and then after that there is a fracture point. So you can see that there are different zones of this behavior, even in one dimension, which need to be modeled in order to get the realistic behavior of the steel. Okay, so this is a jump from the simplest model of steel, which follows just Hooke's law. And unfortunately, I told you that most of the structural engineers, they think that soils are just Hookean material. We call it Hookean material, means it follows Hooke's law only. Okay. Now, what is the simplest form of constitutive law which is applicable to the soils? Now, we have seen on the steel or on other metals or materials. So what is the simplest form of constitutive law that is applicable to soils? I think you people should have, or at least the graduate students should know this thing, that is the Mohawk Coulomb Law. What is Mohawk Coulomb Law? You can see here, this is a Mohawk Coulomb diagram, and on left side of this diagram, you can see one specimen which has a confinement pressure applied by these three arrows. Okay, now what happens at this state? You can see here that this is represented by this one cross over here. You can see the pointer over here. You can see this is the location. Now this is the location, so it is away from the failure line, Now what will happen? We will start with loading it. So as we give more loading on top of the specimen, you can see the stress state is changing. Okay, the stress state is changing. So as I apply more force on it, or pressure on it, or stress on it, you can see the circle has come to here. So it is coming close to the failure line. So if I apply more pressure, and then finally you will have the failure of the material. So this is the concept of the Mohawk Coulomb law. What does it say? What does it say? This Mohawk Coulomb is that the material is elastic before failure, is perfectly elastic, and then it becomes perfectly plastic once the failure occurs. Okay, so there are two now stems of this constitutive law. It is Mohawk Coulomb law, and you can see here there is a part here which is perfectly elastic, and this was all the part which I showed you during the loading. And here, once it fails, and it's perfectly plastic, it breaks like plastic. That's why we call it perfectly plastic. So there is no deformation after, no plastic deformation after that. It's just breaks and fails over here. So this is one of the simplest form of constitutive law which is used by the geotechnical engineers. I have seen 90% of the geotechnical engineers not going beyond it, or maybe 99 might be a good number. So this is, but this is very, very simple. So we'll see that why it is simple and what are the limitations of this law. Should we go more than this, or it's enough for us? This is what we are going to see. Now, where do we use this law? As we are saying, that is.
Can I have a question here? Small question.
Yeah, sure.
Yeah. Once we are talking about this elastic, perfectly plastic model, just for clarification of the students, would you like to explain further something on the limitations of this achieving the limit of elasticity at a very, very small strain level, and that is what makes it difficult to model for soils, because the elastic range diminishes at a very small strain level. So how that is my just point, please.
Yeah, actually, there is, of course, in most of the materials, as you said, the elastic range is very, very small, or in most of the soils, the elastic range is very, very small. So that's why it's almost impossible or very difficult to get that part, or what's called as elastic modulus. The rest is the plastic part or elastoplastic part of the curve. But this is what actually we come up with just to make an average value, okay, of that part. There are I think there is one slide after a couple of slides, and maybe I can explain it even better over there, because there the real behavior, I'll show the real behavior, and then I will try to compare the real behavior with this hypothetical behavior, and why we are taking this hypothetical behavior. We will consider it there. Is it okay, Doctor?
Yes, thank you very much. Thank you.
Okay, yeah. Yeah, I'll come back to that. Okay, so this is so where do we use? Actually, I'm not showing the realistic behavior right now because I want to show where do we use this and what are the limitations of that usage. So where we use, first of all, closed form solutions. Closed form solutions are the empirical relations which we usually use for the bearing capacity analysis, settlement analysis, and other problems like method of slices in slope stability, etc. So there are closed form solution, but we do use in this form of Mohawk Coulomb law in finite element analysis as well. Okay, so I'll come back again at some later stage, but let's look at first of all closed form solutions. What we do, we use the shear failure criterion from Mohawk Coulomb, which is the angle of internal friction and cohesion. And we come up with the bearing capacity from Terzaghis bearing capacity equation using different type of bearing capacity models. And we come up with settlement analysis from other methodologies like Schmertman, and there are others, Verland and others. Now, the most important limitation or the limitation of this usage is that we have a minimum set of parameters and strength and stiffness are predicted independently. Okay, so we cannot combine the strength and stiffness behavior in this form of solution. Okay, we can combine it in finite element analysis, but when we combine in finite element analysis, even the results sometimes remain same. First of all, it show you where do we use these, like we use in slope stability. We have a method of slices, that is a limit equilibrium methodology. And we use the parameters from this constitutive model. We plug in to the methodology, indirect methodology for the slope stability analysis, and we come up with a factor of safety. So that gives us only the strength of this material in the form of a factor of safety against sliding. But it does not give us a methodology which can give us like how much deformation would occur. Okay, so this is the limitation, one of the limitation of this methodology when we use for slope stability, when we use for bearing capacity even. So we will get only the factor of safety against the shear failure, and for retaining wall also the general failure stability of the retaining wall is assessed through closed form solution based on this model. Now this is one of the limitations. Now all these are based on the shear failure analysis or the factor of safety against the shear failure in general. And then we have closed form solutions for settlement analysis. As I mentioned to you, there could be many. This is one of them. And you can see here that we have ES from the model and we have mu from the model, and we directly plug in these two parameters over here to come up with the settlement of any kind of linear structure like foundations, retaining walls, strip footings, wrapped foundations, etc. So this is again a closed form solution where we use these models over here. Okay, but the real behavior is very much different, as Dr. Mubashir pointed out, that we have to look at this one. Even if you look at this plot, this is the real behavior part, okay, which I'm going to show you in the next slide, and you will see over here. So this is the hypothetical behavior which I presented before, and what is the real behavior of soil over here? This is basically the real behavior of some type of soils. Okay, let me flash it again. You can see here, this is the real behavior. Okay, and there are other type of soils that behave in such a manner. So it makes a perfect dolphin. So we call it dolphin behavior. So you can see here all other different type of soils can have infinite type of behaviors in between these two extremes. Okay, now if we look at the behaviors or the constitutive behavior or the material behavior of these two extreme of the soils, you can see it is very much different from the hypothetical model which we usually use. Okay, that's why I have noticed that many people, they use finite element modeling, they use Plaxis, they use Sigma, they use different other software, and they plug in Mohawk Coulomb constitutive model, the hypothetical one. And then they say, see, the results are same as the closed form solutions. So what is the use of finite element modeling? The problem is this, that we are incorporating a wrong behavior model in a highly sophisticated tool. So that will definitely give us the same result as we are getting from the, more or less same kind of result which we are getting from the closed form solutions. So that's why it's very important that we should have the realistic model so that we can define the realistic behavior. And this is very common. This is very common among geotechnical engineers. It's very common among structural engineers. They try to just undermine the importance of constitutive modeling or the finite element modeling. And they say, see, your sophisticated models are giving almost same results as we can quickly get from the closed form solutions. So there doesn't seem to be a requirement of going for such kind of modeling. So the problem is this, that they are not understanding the real model of the behavior of the soils. You can see here, if I divide all these this behavior, I divide it into different parts. You can see up to certain extent there is an elastic zone, then we have a plastic zone, and then we have a peak, and after that we have a fall in the stress levels with the same strain levels. So we call it strain softening zone, and this is very much typical for many type of soils. This behavior is called as strain softening behavior. Okay, but here in this model there is no strain softening behavior. You can see just perfectly plastic. Okay, so I'll show you what effect it creates: the plastic part, the strain softening part, and finally the residual part. But some of the soils, there is no elastic zone over here. But some soils, like for example hard clays and very dense sands, okay, there is very small part which we can call it elastic zone, up to where the strains would be completely reversible. After that, immediately they start taking up the plastic strains within themselves, like over here. Okay, the elastic part over here, little bit exaggerated, but in heavily over consolidated clays or hard clays, this elastic zone is present. But in most of the cases, this is absent over here. Okay, so that's why just we take it a initial tangent modulus, and we just consider it as ES in our simplistic constitutive model based on Mohawk Coulomb theory. Okay, so this is how the behavior is different. Now the soil is a highly complex type of material. This is not only one abnormality associated with it. There are many other abnormalities that are associated with it. If we consider like other civil engineering materials like concrete, steel, and metals, soil is far more complex than these materials. So the people who spend lives in understanding the constitutive models of concrete and steel, I don't know, I mean, how we can grade soil behavior in this regard. Okay, so just to give you more flavor of the complexity of the soil behavior, you can see here, this is one of the dot modeling of the different parts of a triaxially loaded specimen. You can see here, this is the unloaded specimen. So as soon as we start giving stress to it, you can see the different parts are being stressed at different levels. Okay, you can see the blue ones, the green ones, and different parts are getting stressed to different levels or strained to different levels. So this is again because of the nature of the material present at each point among all the specimen. Like for example, I think graduate students can easily understand or appreciate that one, that that for sands, the confining pressure gives the strength of the material. Okay, or for the granular material or non-cohesive material, confining pressure is a very important factor in defining the strength of a material. Now, if we talk about the material at this point, if you talk about the material at this point or this point, each will have different strengths. So some points will fail earlier, and some point will take still be taking higher stresses. So this is how a complex variation of stresses and strains within a small specimen of soil are present. Moreover, it's very important to understand like what happens when we stress the soil. Okay, like for example, if I have a loose or normally consolidated soil, before shearing you can see these are the particles. So I have prepared this animation just to make things more clearer. So once we shear it, you can see here there will be a compression of the material. Okay, compression of the material, and then if I further shear it, there will be rotation of the material, and finally they will reach at a state we call it parallel or critical state. So see here, from shearing to this parallel critical state, the soil particles go through different distortions. Okay, depending upon whether it is a loose soil or dense soil. For loose soil, this is the behavior which I have shown you, and for dense soil, you can see here we have a, before shearing you can see the dense state, the particles are very close to each other. When we shear these particles, you can see there is a dilation occurring over there. Okay, so this dilation makes its peak strength very high, and then rotation, and finally you will see at the same state. Okay, so if I just go back to, after showing you this one, if I go back to this one, now you people can well understand that this is the behavior, the upper part of this one is a behavior which is for the dense material. So you will have a higher peak, and then dilation, and then there is dilation, and there is a compression, and finally it reaches at one point. And if we took at loose soils, these are keep on compressing themselves and reach over here. So there is no dilation over here. So this is another very specific property of the soil that make it different from the other different materials. And this you can now, I think, well imagine that if you have a part of the material over here is dense and part of the material here is loose, so you can easily see the difference in behavior during the stress strain modeling. Okay, so just for the sake of understanding even the closed form, some of the closed form solutions which we use very, very confidently, you can see here, this is the famous Terzaghi failure criterion. But if you look at this one and consider the real behavior of the soil, like this one, not like elastic and perfectly plastic, up to here we have a K0 value, and then we have a highly non-linear behavior. So if you look at this one, when we do analysis based on Terzaghi's theory, we consider there is a plastic failure along the whole length of this line. Okay, but this is not true. This point over here is still maybe very close to the elastic line, and here you can see it has moved to elastoplastic line. This point has already crossed the peak behavior, and finally you can see here it is very close to maybe the residual behavior. So this makes even the most simplest form of solution, which we closed form of solution, we just imagine based on a certain experimentation is not the realistic behavior. Okay, so this is one of the case, and in many cases, in many geotechnical problems, we have importance of not only of shear failure, we have high importance of deformations, and this is what is usually people omit during the analysis. We go for the shear. Sometimes we have a very high factor of safety against shear, But till achieving that high factor of safety, we have a lot of deformations in the structure. So it's very important to combine the deformation and shear behavior together. And this is only possible if we use advanced type of constitutive models or the realistic type of constitutive models which I have shown you. Okay, some of the examples are like, for example, anchor pull-out. Now, anchor pull-out is consists of two things. Like, one is the shear capacity of this part of the anchor, and other how much it has deformed. Sometimes we don't care whether there is a failure occurs over here or not, but we do have a serviceability limit of the anchor, and if it is within that one, we can accept it. So similarly, you can see the tie pull-out. I have seen most of the geotechnical engineers and almost 100% of structural engineers calculating the capacity of the wall just based on the shear failures, on the active and passive and at rest conditions. But here, the most important part of any shear wall, any retaining wall, sorry, is the movement of this wall with respect to the material behind it, and this is very, very critical information that is required. And for tunnel excavation, okay, so it's not only the shear failure of the tunnel material or tunnel walls or tunnel roof, it is the total deformation that tunnel will experience. So this is very important to combine these together. And you can see another example. I mean, there are a lot of other examples. I'm just giving you some of these. Like excavation of vertical shaft or sinking of caissons. It's very important that whether there will be an instability like this one, and how much will be the movement of the sides of the hole, because that's very important to determine the real capacity of the pile foundations. Okay, with this one, I'm just going to list down all the different factors, which basically, when we combine together, define the soil specific behavior. Okay, now state of stress, as I told you, is very important. If you have a high stress around the material, its behavior will be different. If you have lesser stress around the material, its behavior will be different. Then we have compressive and shear coupled strains. Now, I mean, other than like civil engineering materials, or you can say if we exclude all other materials, the soil is very unique. Soil is very unique. When we apply stresses on it, always there is a compressive strain and a shear strain introduced at the same time. So that's why coupled strain analysis is very, very important for the soils. Okay, so this is very much unique to the soil behavior. Other materials, some of the other material may have, but most of the materials, they don't have this kind of behavior. That's why you see, that's why a very important question always we ask the students, that why we use a compressive strength of concrete and we say shear strength of soils. Okay, we don't say compressive strength of soil. So this is the reason, because the shear strains are always taking place hands in hand with the compressive strain. So that's why this is again a unique behavior. Residual or initial pressure is very, very important in a case of soils. This is absent in concrete. I mean, concrete does not register any history, but soils do register a history. If we just compress the soil for some time and leave it, it will definitely have some effect which will be represented at the later stage of the of its life, or stress life, you can say. We usually use terminology pre-consolidation pressure or over-consolidation ratios in this regard. So that's very important, but I don't want to use this terminology because this is much more than that. So residual or initial pressure is very, very important. There are several possibilities. There are several possibilities of having residual stresses in the soils. Now, volume change under shear, which is called shear dilatancy. I've shown you from the real behavior, one of the real behavior plot, that there is always expansion in the soil volume when it is stressed or strained, if it is present in a dense form. So this behavior is known as the shear dilatancy. Then there is swelling and shrinkage strains. Now these are independent of the external loading. There are different type of soil minerals, soil particles, which swell and shrink when water is provided to them or water is taken out from them. So we call it swelling and shrinkage strains. Sometimes these also required to be coupled with it. Okay, then we have inherent and induced anisotropy. We call it progressive failure. Now, inherent anisotropy is, of course, because of the depositional environment, because of the different stress level, different kind of pre-stresses on the soil. So this could also be there, or the depositional environment is producing different type of seams and different type of grouping of particles at some place and different other type of particles grouping at other place. So we call it anisotropy. But here we could have induced anisotropy. This is because of the stress level. We can have a high stress level at one point and low stress level at another point. So that's also an anisotropy, and that sometimes lead to progressive failure. We can have a weaker material and we can have a lesser confining pressure. So the failure would initiate from here. Okay, you just keep these terminology in your mind. I'll be going to present you one case history shortly, and I'll show you all these the aspects or the behavior aspects in that case study. Okay. Change in physical state, of course, cementation, and then breakage of cementation, then presence of one type of fluid and presence of other type of fluid. This also changes the behavior of the soil. Change in port fluid from water to other fluid, and then this is again very important. This is drained versus undrained. Okay, soil behavior. Most of the soils, the behavior is well controlled, whether it is drained or undrained. I don't know, I mean, as graduate students at least, you people can well understand that we allow excess pore water pressure to dissipate. We call it drain behavior, and we don't allow or the stress scenario is such that it does not allow dissipation of excess pore pressure during the loading period. We call it as undrained behavior. Okay, one more thing, which is long versus short-term behavior. This is also very important, and it is somehow related with the drained or undrained behavior, but there could be other changes like creep or torsion-related issues. But again, there are certain phenomena associated with the long-term behavior of compressive soils and long-term behavior of dilating soils, and short-term behavior of dilating soils versus long-term behavior of soils under compression. Okay, so this is not to teach you something new, just to give you an idea that how many factors are there that need to be understood, incorporated in a behavior model, so that we can get the real behavior of soil. Okay, it is much different from the behavior of any other civil engineering material. Okay, now how to incorporate, how we can start incorporating all these behavior in a. So we can look at this plot again, which I showed you earlier. We saw that we should define. Now we have to translate this plot into a mathematical model. Okay, so in order to translate into a mathematical model, we have to define different zones, first of all. And then we have to define the mathematical model of each zone, how to get the parameters for that zone, and then how to define the mathematical model. This is the essence of constitutive modeling. Now, in this lecture, I'm just going to give you a general introduction, okay, a general exposure, how we do it, but there will be no specific modeling details in this lecture at least. Okay. But of course, if we talk about one single constitutive model, it requires at least a couple of lectures to understand how we go about the complete modeling part. Okay, so I'm just going to give you a very general idea how a constitutive model looks like, which I have given you. Now, how we translate it into mathematical model. Okay, and that mathematical model is then used in the digital modeling, in computer modeling, to give us the response. Okay, so this one we have to define elastic zone. This elastic zone could be something, or it could be zero. Okay, for some type of soils it's zero, and for some type of soils it is there is a finite limit for this one. Okay, then we enter into another zone after the elastic zone is over. That is known as the plastic zone. Okay, so first of all, elastic zone, then we have plastic zone. So I have already given you a very general definition of plastic zone. Here, any unloading of the material, there will be a permanent settlement. There will be permanent settlement of the material. Now, material has yielded. This A point, usually we called it the yield stress or the yield point. Okay, so up till elastic limit, we have a yield point, and after yield point, your material has entered into a plastic zone. Finally, it reaches at the top, which is basically the peak. And after peak, most of the material, they strain soften. We call it strain soften because there is a reduction in stress with further straining. Okay, so this is the strain softening zone. So you can see here we need a mathematical model for elastic zone, and we need a mathematical model for plastic zone. We need to define points B and A, and we need to have a mathematical model for the strain softening zone or the post-peak behavior zone. And finally, there is a residual zone. In most of the soils, we also classify a residual zones. Okay, so we'll have a residual end limit, and we have start of the residual zone and the peak zone. So if we can define all these A, B, C, D, and we can have these limits, and then we can define mathematical models that can follow the curve or the behavior within this zone. We can combine these to come up with the complete constitutive model or constitutive behavior of that specific behavior. So we have a pre-peak elastoplastic deformation zone, and we have a post-peak rupture zone. We call it post-peak rupture zone. So this is a very, very general understanding of a typical constitutive model for soils. Okay, now I have just told you about I have just used, you can say, the qualitative terminologies like plastic zone. But how to define plastic zone whenever we are talking in terms of mathematics? Okay, so let's see in the next slide. I have just brought this one in the smaller part. I hope you can see these, or at least you can remember which zones over here. And I'll show you a table over here. Like if you now compare the elastic behavior part, which was represented by the Hooke's law only. Okay, Hooke's law only. And plastic produces elastic strains. So in addition to now the elastic behavior, or the most simplistic model, constitutive model, we have introduced now the plastic behavior. Now the plastic behavior consists of all these 4 different zones, okay, or 4 different endpoints or 4 different zones. Now, what exactly we have to define? If we can define all these 4 in terms of mathematics, we can couple these together with the elastic part, and we can define the complete behavior of the soil. Okay, now what are these? Like for example, you can see here, you can have here yield criterion. So where is the yield criterion over here? You can see here, this is the yield criterion. Okay, this is the yield criterion. So we have a yield point here, and we have to define what is the yield criterion. Now in mathematical terminology, there will be a relationship. We will call it yield criterion, which will define the yield point. Okay, so determines when the plastic strain increments occur, only when yield surface is pushed out in hardening software. Okay, so this is the yield criterion. So this is the first, in addition to the Hooke's law, which is the elastic part, will the first set of mathematical equation would be the yield criterion that will define the yield point or the yield surface in 3 dimensions. Okay. So the next is basically the failure criterion. So we'll have a failure criterion, and this will define the when this point in the soil fails. Now this is again a highly subjective terminology. Highly subjective terminology, because failure is subjective. Maybe for some of the cases, complete shear failure could be failure, or a 1-inch settlement could be a failure. Okay, so failure criterion again is highly subjective, but we have to define for our soil what we call it as failure. Okay, then the third part is basically the plastic zone. Now, plastic zone is represented by a function, mathematical function. We call it plastic potential function. Okay. Again, I'm telling you that I'm not going into details of each of these, but just I'm introducing that how many parts we have to study, how many parts we have to experimentally determine, and then translate into mathematical form, and finally into a computing form. Okay. So we'll have yield criterion, failure criterion, then you have plastic potential function, and finally, this part, which is basically now flashing, you can see here, this flashing part is represented by hardening or softening relation. Okay, so there is a relation, mathematical relation, that will give us the complete behavior of this part, which is called stress softening part or hardening part. Okay, so if we do have these 4 relationships, our constitutive model is complete. Otherwise, we'll be just sticking to the Hooke's law, which is the simplest part. So now you see here how we have transformed now from a perfectly elastic behavior to a complete plastic behavior of the soil. Okay, this is clear. Now, how we go about it? We have seen already that how we have defined these things now. So you have seen the Hooke's law, and you have seen the Mohawk Coulomb criterion, and we have seen the different plastic behaviors. Okay, now there are different models. There are different models that exist for defining the behavior of concrete, steel, and other metals. Sometimes people use these models for the soil also, but it is I think not justified to use these models for the soil. But I will just give you an idea. And now you have seen the concept. You have seen how many relationships you require for defining the elastic, elastoplastic, peak, and post-peak behavior. Right, so there are 4 things. Now look at any simple model. This is now the Mohawk Coulomb in 3 dimensions. I think before today you were just looking at it in 2 dimensions, just this line, right? This line. Now this is in 3 dimensions, where you have sigma 1, sigma 2, and sigma 3 all combined. So you can have a point inside anywhere in this surface. Okay. Till the time this point is inside this surface, it will be in elastic form. Once the combination of sigma 1, sigma 2, sigma 3 moves this point on this surface, anywhere on this surface, there will be perfectly plastic behavior. Okay, so this is the 3-dimensional concept of Mohawk Coulomb. Okay, similarly there is Drucker-Prager. Now instead of this hexagonal shape, it is circular in nature. There is a strain hardening cap model. Here it is different, little bit different. In this case, I don't want to confuse you with so many terminology. There is no expansion of the yield surface. So yield surface is fixed. There could be other models like strain hardening cap model. The yield surface expands. Okay, so it's a continuous movement of the stress point on it till it reaches the failure, and then it defines the post-peak behavior also. Okay, but despite some complexity, some real behavior associated with Laird and Duncan model and strain hardening cap model, still they are I think very close to these other 2 models. So I'm just giving you the name so that you people can remember that other than Mohawk Coulomb is Drucker-Prager, very famous model for concrete modeling, and these two models are also used for steel in defining the behavior of steel. Okay, but people are using these models for the soil, but it is not justified. If you consider all the factors which I listed before, and if you consider all the specificities associated with the soils, you can easily say that these models are not applicable. Okay, or even if these are applicable, we have to use the results with caution. Now, what type of models usually we use in soils? Okay, the first model, which is a next step to the Mohawk Coulomb, which is elastic, perfectly plastic, is hyperbolic model. Okay, you can see here, this is, if I just follow my this pointer, you can see elastic, and this is perfectly plastic. But now this model, the solid line, you can see the solid line is basically a hyperbolic model. Now in hyperbolic model, it's all elastic again. It's all elastic again, but it is, we called it hyperelasticity, where there is a curvature in the elastic part and it reaches to the perfectly plastic zone, but all this zone is still under elastic strains. So usually we call it hyperbolic model. So this is also a form of model that is a step ahead of Mohawk Coulomb to define the behavior of soils. But this behavior of soils, as you have seen in the previous slides, that is controlled by one more parameter which is not applicable. I don't know whether you people noticed or not. Now I want to emphasize, there is one parameter which is the density of the soil. Okay, that's why I have shown you so many examples where density plays its role. So that's why the first real model that can be considered as the real that depicts the real behavior of the soil is CAM-CLAY model, with density as a state parameter. Okay, I'm going to show you this one. Initially, it may look quite complex to you. You can see here there is a shear stress on this line, and on this axis we have the normal pressure. So if you look from this side, it is nothing else but a Mohawk Coulomb plane. Now on the third axis, you can see here there is V, which is basically representative of the volume of the soil or the density of the soils. Okay, so this is very, very important. If I just make it 0, you can see all this will collapse to a simple Mohawk Coulomb criterion. But if we just expand V, you can see different parts of this model. Now, each model, as we have seen previously, is basically a surface. Okay, till the time you are under the surface, or combination of P, Q, or V keeps you under the surface, you are in an elastic state. As soon as you touch this surface, this is a yield surface, and then you will have plastic deformations, and finally you move on the yield surface to the failure line, which in this case is known as the critical state line. Okay, so I'll just give you, for example, if the point is here, then it will move up till the time it touches the surface. It is in elastic state. Then it suffers plastic strains, starts suffering plastic strains as soon as it moves along the yield surface, and finally it reaches the failure. Okay, and if you have a normally consolidated line, there will be no elastic part. It will start moving from this line directly. It will graze on the yield surface and it will reach over here. Okay, I think you can combine these two behaviors to understand the two real curves which I showed you before. Okay, so what do we need to define it mathematically? We require an elastic part, we require the yield criterion, we require the hardening and the softening part, and we require the maximum stress criterion. Okay, so if we combine these 4 mathematical laws for this type of model, we can have a realistic feel of the soil behavior. Okay, now how do we use? We have seen that Mohawk Coulomb can be used for finite element, but generally it is being used for the closed form solutions. Okay, so here we have like the now split up classification. If we have simple type of models, and these models we can get parameters from very simple laboratory tests, like for example these parameters C, pi, E, and mu, which we have seen, and we will use these in closed form solutions. So all the simple models will follow this line, but the advanced models we require, like for example all these complex type of tests like isotropic compression, triaxial compression, etc. And the parameters I'll show you later on, the highly complex parameters, and number of parameters may reach 20, 30 sometimes for a very complex type of constitutive model. And finally we will use them in finite element modeling. Okay, so these will never be used, and they cannot be used. These type of advanced models and their subsequent parameters cannot be used in closed form solutions. Okay, so we have a split up. The closed form solutions I've shown you, and I have given you a flavor of the understanding of a constitutive model for general materials like Mohawk Coulomb, Drucker-Prager, etc., etc., and the flavor of or vision of, I can say, vision of a 3-dimensional constitutive surface for the soils, like CAM-clay model. Okay, so where do we use these? Now you can see here just a very schematic sketch showing that this is a finite element sketch, and we have one small finite element. What happens over here? We have combination of the elastic model, one type of plastic model, other type of plastic model, other type of plastic model, and finally the boundary conditions, and we come up with this stress strain curve. Okay, so what is happening inside a real finite element analysis is much complex than what usually we see. So we do have otherwise we have E, and we have just the final one, and we say, oh, we have run the finite element analysis. No, there are many criteria that are involved. One is the failure criteria, other is yield criteria, then elastoplastic hardening, then maybe softening, and finally combining it with the boundary conditions, you come up with the real behavior. So this is the concept which is there in case of finite element. Okay, now I will show you one glimpse of a finite element analysis for one of the example first, and then I will show you a complete case study that will I think reinforce the concept which I have tried to develop today.
Okay.
Yes.
Just one question can I have here?
Yes, sure.
If you go to the previous slide, sir. Can we explain to the students the basic difference between finite element analysis and a discrete element analysis, so that they can understand from this point and onwards that what is the basic difference between these two models?
Okay. Basically, Dr. Mubashir, I have a slide, I think after maybe 10-15 slides, where I have given a difference between the continuum, the discrete element, and the molecular level modeling.
Okay.
Should I give it right now, or?
If it's there, it's okay. We can have it.
Yeah, it is there. Okay. So I will recall this over there. Okay.
Thank you.
Because I think that will give, like, because this is for the continuum. For any continuum material, we go with just divide it into finite elements, and we define the behavior of each element and the connectivity of the elements, and that constitutes the finite element analysis of continuum materials. But if the material is such like soils, it's very it's highly unjust to call soil as a continuous material. It's basically granular material. Okay, so in order to define the behavior of this granular material, sometimes or most of the times we use or we consider it as a continuum, and then we go with the finite element analysis. But the real behavior of the soil, as Dr. Mubashir pointed out, can only be done using discrete element analysis. Okay, I'll show you some of the slides which will give you more idea about this one. Okay, so here we are considering, like, it's justified to use it for concrete. It is justified to use it for any steel structure, and consider it as a continuum material and divide it into finite elements, and then defining the behavior of each element and superimposing the results. But for granular material, yes, that's right, that we have to go, or if we want a realistic behavior, we need to go either to discrete element modeling or to go for the real molecular level modeling. Some of the soil particles, their behavior, it's very unjust to consider it as a continuum, because all the reactions take place at molecular level, and I'll show you some of the results in this regard also. Okay. Okay, this is just to give you an idea. Like, for example, this is a finite element of retaining structure with the anchors, and you can see here that the results show part of this. The results show not only the shear failure, which we are always after. It is showing the deformation that should be expected during the service loading. Like, for example, there will be some movement of wall in this direction, and there will be movement of the base of the excavation also over here. So without using the real constitutive models, we cannot predict all these things in a precise manner. Okay, so this is just one example to start with. Now I'm going to present you a case study. Basically, it's related with the slope stability of soils and rocks. And it's a comparison of finite element methodology versus limit equilibrium methodology, which we usually use for slope stability analysis. And I have used Sigma W software for finite element analysis and Slope W software for limit equilibrium methodology. And this case study I presented in one of the seminar at UET Lahore in 2005. So it's only 15 years back I presented this case study. Okay, so in this case study, actually we prepared 3 different models of slopes. So model number 1, model 2, and model 3. In model number 1, you can see here we have 3 different layers, and the height of the slope is 35 meter and the angle is 45 degree. These layers, the first one is highly weathered sandstone, then we have highly weathered shale, and finally we have sound sandstone at the bottom. Okay. Now for model number 1, for the analysis in finite element model, I used elastoplastic model. Okay, and then for limit equilibrium, the Mohawk Coulomb model was used. Okay, so this is it's a more realistic finite element, and we have Mohawk Coulomb for the limit equilibrium analysis. All of you should have a good idea that whenever I'm saying limit equilibrium for slope stability, it is method of slices. Okay, with the least complexity to the high to the maximum complexity, there are different methods available. Okay, now this model number 2, I have sandstone, I have shale, and I have then again sandstone. So their weathering extent is lesser over here. So I have higher shear strength parameters for sandstone and shale. The first one was weaker model, and this one is. Now in this one, the finite element I have used strain softening model, and in limit equilibrium again Mohawk Coulomb methodology. In model number 3, I have introduced a soft clay layer over here. You can see, you can just follow the pointer. This green layer is basically a soft shell layer. So I have same sandstone, I have shale, and I have this layer over here. And finally, the base material is again sound sandstone. In this case, I used the same models which I used for the first model, which is elastoplastic for finite element, and Mohawk Coulomb model in case of limit equilibrium. Now let's see the results, analysis and results. So model number one, the limit equilibrium analysis. You can see here, this was done in Slope W software, method of slices, and the factor of safety is 0.96. So if the parameters which I used for this one is showing that the slope should fail, okay, if I use limit equilibrium analysis. Now if I go for the finite element analysis, now I don't want to go into detail about this one, about this model, but how we measure the factor of safety. But just to name it, we call it increase in the stress level methodology. We increase the gravity load and we see at what gravity load the failure occurs. So this is known as incremental gravity load methodology, or increase in stress level methodology. So there are different names being used for that one. So this is the model you can see here, the strain model at 100% gravity load. You can see here some part of the model here, light greenish color. There are higher strains than the other part of the model. So it shows that there is some localized failure being started over here, which the terminology which I used as the progressive failure. In the next one, you can see here at 110% gravity load, you can see now the strain level is even higher over here, and the strain path, weaker strain path is moving in this direction. Okay, with further 115, you can see here. 115, you can see here some part has reached a peak. Okay, at 150, and at 120%, you can see the part of the slope has ruptured. Okay, still you can see there is no failure over here, but now failure has occurred over here, and this slope will slide at 120% gravity load. So the factor of safety in case of this slope should be 1.2. This is how we define the factor of safety. I don't want to go into detail, but I'm just giving you an idea. Okay, for model number 2, you can see here for model number 2, as I mentioned to you, because I use strain softening. When I say use strain softening, there is a strain hardening. So there are peak values and then there are residual values. So when I used peak values, the factor of safety was 5.99, and when I used residual values, again the factor of safety was lesser than 1. Okay, so so this is again quite confusing. Sometimes people say no, I should go for residual values, but if the slope hasn't moved much, you cannot use residual values. You have to go for the peak values. So peak values is giving a very high factor of safety of 6. Now let's see what happens when I used finite element analysis. So 100% gravity, you can see 115%. The slope is moving 130%. Even the strains are higher over here, 145%, 160%. Still there is nothing. I can see now it's reaching to the close to the peak, and still 215%, 230%. You can see it has reached almost the peak. Now there will be stone softening part, and this is where the rupture of the slope occurs. Okay, so you can see here that the failure of this part of slope was considered as the critical under finite element analysis, while limit equilibrium was giving something else. Okay, which is highly hypothetical. So now the factor of safety in this case is 2.45. Now, although if you look at this one, there is always in finite element analysis, there is always a movement analysis going on in parallel to the shear failure. Now the shear failure is giving a factor of safety of 2.45, but if you look at the deformed shape of the slope, you can see here all this part has been yielded, and you can see the movement at 2.4 factor of safety. There is a lot of movement of the slope. Okay, so this is how the movement is very important. Movement calculation or evaluation is very important along with the shear failure. Okay, I'll give you a summary at the end, but right now just be with me. In model number 3, we can see here the limit equilibrium factor of safety is 3.4. Now you remember I introduced this soft shell layer. So this soft shell layer reduced factor of safety of 3.5 for in limit equilibrium. Now you see here, now in limit equilibrium, you know the failure surface will pass like this one. So very small part of the failure surface is passing through this one. And it shows that the contribution of this layer should be very small in the overall stability of the slope. But this is not the case. If we look at the finite element, you can see even at 75% there is peak failure, or the progressive failure I told you before started over here. So here you can see up to 100% there is a complete failure, or lesser than 100% gravity load there is a complete failure in this layer only. The all other slope is intact. So, but overall, the slope has definitely failed. Okay. So now, if I look at the summary, I showed you the summary of all these models, 3 models. You can see here that these are the factor of safeties from limit equilibrium methodology, and these are the factor of safety from finite element models. So, in the first case only, limit equilibrium methodology is conservative. In other 2 methodologies, limit equilibrium method, use of limit equilibrium method is highly unsafe. So this shows, because usually I have seen people calling, oh, no problem, I can use indirect methodologies, I can go for closed form solutions, I can go for limit equilibrium methodologies, my results would be conservative. But this is not the case every time. Okay, so that's why it's very important to go for finite element methodologies for many cases which we cannot understand whether it will go towards a conservativeness or it will go towards a highly unsafe situation. Okay, so this is what is related with a case study, I think, and as I mentioned to you before, that there are different parameters. Now, the question always arises. I'll just give you again an idea that what type of parameters required for these mathematical models. I have given you just the nomenclature like yield criterion, and I've given you like strain hardening law, strain softening law, failure criterion. But how do they look like? I'll just show you how do they look like and how many parameters usually required to define a good constitutive model. So you can see here there are 3 comparison of 3 elastic perfectly plastic approach, which is Mohawk Coulomb. This is modified cam clay model which I showed you, and there is another model now called single hardening model. Okay, single hardening model. So for elastic perfectly plastic, you can see Hooke's law is just used over here. This is E and U is required, and finally for failure criterion C and phi is required. But if we look at the corresponding parameters for modified cam clay, we require 2 parameters to define the elastic part. We require 1 point to require the failure criterion, and we require 2 parameters to define the hardening or softening for relationship. Okay. So this is the case. Now, if we look at the even the more advanced model or model much advanced than the modified cam clay, you can see 3 parameters are required to define the elasticity part, another 3 for the failure criterion, another 2 for the plastic potential, and 2 for the yield criterion, and another 2 for the hardening softening relationship. Okay, so you can count these as at least 12 parameters to define the behavior. But for modified cam clay, there are 5 parameters that can define the complete behavior of the model. Okay, so in this respect, I'm just going to give you. I think this can be given as a handout to you. The comparison of different kind of models. This one, you can see here in this one I have a list of simple elastoplastic models I mentioned to you, and you can see here many models over there. You can see even Mohawk Coulomb, Plexus soft soil, Leyd and Duncan, Drucker's cap model, stress dialysis density, and hyperbolic model in the elastic range. I showed you Hooke's law and hyperbolic model. So this table can provide you for your future reference just whether the applicability of these models on different type of soils. Like for example, is this model applicable for sand, clay, and cemented soil? Yes, yes, yes. So you can see this one. Then what type of failure surface each one of these uses? For hyperbolic, this is Mohawk Coulomb, and even for plexus soft soil, the Mohawk Coulomb is their failure surface. And then comes yield surface. So different type of yield surfaces like spherical cap, Mohawk Coulomb, elliptical cap, and smooth, triangular, conical. And for hardening parameters, you can see here there's a plastic work, plastic volume, volumetric strain. It's a complete subject actually that we are looking at right now in just few slides. Okay, so this was the list of simple elastoplastic. Then this is the list of models which are based on critical state. So I defined this critical state in one of the animation earlier. You see here now modified cam clay, elasto-viscoplastic, then you have structured cam clay, anisotropic cam clay, and even the unified SMP. So the references are there, the type of soil on which these are applicable, the failure surface for each one of these, the yield surface, the hardening parameter. So this is how you can have an idea whenever you are involved in any research related with constitutive modeling. Here there are how to determine the parameters for different type of or some of the models which I have listed in the previous two tables. You can see here this is a list of models over here, and here the experiments for parameter determination. Like for modified cam clay, you can see here 3 triaxial compressive and 1 isotropic compressive strength test is required. Okay, so that will provide the total 5 parameters which I showed you before. Now, just if I want to show you another one, like for example, structured cam clay. So 3 triaxial compressive strength and 1 iso or K0 compressive strength tests would be required, and there are 10 parameters which you will assess from these set of tests. Okay, I assume that you people should be well aware of what is a triaxial compressive test and what is K0 compressive test and what is CU or CD, etc. Versions of triaxial compression testing. Okay, like for example, now for anisotropic plasticity, you can see a big, a long battery of tests would be required to get these 8 parameters. Okay, so basically lab testing would be required, and we call it macroscopic testing would be required to achieve these parameters for each type of model. Now, if I move into further advanced models, which I don't want to go, but just to introduce you, we have incrementally nonlinear, we have multiple surfaces, and we have double hardening models. And like their previous counterparts or their younger siblings, you can say, again, you can get all different kind of information like type of soils, failure surface, yield surface, etc. for this one. And then again, this is a list of more advanced models like bonding surfaces and single yield surfaces, etc. And how to get parameters for this one, you can see here. Now for these more advanced models, the most critical step is the acquisition of the parameters. Like for example, for MIT E3 model, you can see here so many triaxial tests are required in addition to the resonant column tests also. Lateral stresses, resonant column tests also. And you require 15 parameters to be determined, and in this case it is 17 parameters. Okay, so these are the tests that would help you in defining this one. Okay, so this is what I wanted to discuss regarding the constitutive models. We usually called it based on the continuum concept or the continuum mechanics. Okay, when we are considering soil or the material as a continuous material, there is no boundaries in between the materials. There are boundaries only on the exterior surfaces of the material. So that material we called it as continuous material. As Dr. Mubashir pointed out, that we need to know that one. Now there is a new dimension in the constitutive model.
Doctor, just before you proceed, I just want to add one comment over here for the students. आपने यहाँ पे MIT S1, MIT S3 models और CAM clay models देखे हैं, तो you should be familiar that this MIT is actually referring to the university MIT in the United States. And similarly, that CAM clay model that comes from Cambridge, CAM for Cambridge. तो आपको बताने का मकसद ये है कि हमारी जो मटेरियल कैरेक्टराइजेशन है और उसकी कॉन्स्टिट्यूटिव मॉडलिंग है, that all depends on how much experimental work you have done on your local materials in your experimental setup. So unfortunately, आपने देखा होगा कि हमारे regions की जितनी भी soils हैं, they are unexplored, they are unmodeled, they are untouched, I would say. So there's a lot of space and I would say opportunities available for the students to come up with these kind of advanced testing, and they can develop models for local materials, and so that we can understand their behavior much better than what we have been using by the foreign materials, I would say. That is a comment I want to add over here for the students.
That's perfect. Okay. So as Dr. Mubashir, I think rightly and timely pointed out this thing, that a lot of effort is required in order to develop models for the local soils. Okay. Now there is a new dimension that's, I think I can just stem from what Dr. Mubashir said, that for the continuum models, definitely, and the type of soils, specific type of soils available in each area, other than the Cambridge or MIT or other regions of the world where these models have been developed, we need to definitely address so many parameters, or we have to come up with a specific testing program to come up with specific parameters for our models or models applicable to our type of soils. Now this new dimension in constitutive modeling is there, which once done develops a universal type of model. I mean, there is no need for doing specific testing or testing of the specific soils in the region. It develops a model which is now independent of the regions, independent of the specific areas, and we can have a behavior of a soil. We can use these models to predict the behavior of a soil present anywhere on the surface of the earth, I will say. Okay. Now, what is the concept and why these are universal in nature? This is what I'm going to discuss in the next few slides, and that will conclude my lecture, inshallah. So, what is the new dimensions? We called it nano level constitutive models, and these nano level constitutive models are based on the molecular level simulations and modeling. If we just concentrate or just try to vision with me that all the soils or all the material, the behavior, the external behavior or the macro behavior, the behavior which we see at the surface of these materials, it basically originates from the atomic or molecular level. Okay, so if we are capable of doing atomic level or molecular level modeling, simulation first and then modeling, we can have a universal model that should be applicable under all kind of conditions. Just we have to plug in the basic parameters, very basic parameters in it, and we can come up with the behavior of a soil present anywhere on the surface of the earth. Okay. Now, what is the concept? This will define. Dr. Mubashir wanted me to explain this thing to you as sometimes earlier. Now I'll show you over here. The models which we have seen so far are based on the understanding or based on the assumption, I'll say assumption, that our material or the soil is continuum in nature, which is not true. Okay, it may be true, although I don't agree with concrete people that it is true for concrete. Even concrete is not continuum. None of the material on the surface of the earth, including steel, is not continuum. There are atomic bonding. There is atomic bonding present inside the steel, and different type of bondings are present inside it. Some are the weak bonds, some stronger bonds, etc., etc. Even the necking behavior of the steel, or the failure surface of the steel shows that steel is not a continuum material. Okay, I don't want to go into detail, but I just want to give you a message. Okay, but we are forced to consider as continuum material because we need simplicity. We cannot go into advanced modeling every time. Now, in case of soils, we have generally two different type of particles. One say granular particles, in which the interaction is mostly physical in nature, and we do have a component of soil. We call it plastic material, where the interaction is not only physical but also chemical in nature. Okay, so that is, if we do have granular material, maybe we can better classify using the particulate mechanics principles, okay, rather than the continuum principles. So if we develop a model based on this one, and we can define the different shapes of sand particles, different shapes of silt particles, different shapes of gravels, and different sizes of gravels, and different packing of gravels, we can develop a universal model based on the particulate mechanics principle. Okay, we will apply all the physical rules on this one, and then the constitutive behavior will automatically come from within the model. Okay, and same is the case for the models for the clays, where the behavior is controlled at the molecular level. Now, in case of clays, we can do molecular level modeling, or we can do molecular level simulations first, and then we can develop a model that should be universal in nature. We will just need to plug in some of the very basic parameters of the clay constituents, like mineralogy, like its cation exchange capacity, its other chemical properties, cementation, etc., and then it will give us a very appropriate result or outcome from this model, or a response, we can say, response from this model. In fact, my PhD was on developing a universal model for the clay soils, and using the molecular level simulation principles, myself and my advisor, we did so much research on it, and we were able to develop I will say, complete universal model for the clay soils. And this is applicable to all the soils also, where the clay is controlling the behavior. Not necessarily that it is fully composed of clay. Even if you have 70% sand and 30% clay, and the behavior is controlled by the clay component of the soil, this model should be applicable. Now, I'll give you again very general highlights. I will say highlights of this research to give you an idea that how it can be carried out. We started with a single clay mineral, and you can see here how small it is. Even human naked eye cannot see it. Only it can be seen through electron microscope indirectly. You can see here this bar is almost 30 angstrom. It is just 30 angstrom, and you know, 1 angstrom is 10 raised to -1 nanometers. So it's how small this particle is. So the behavior of clay particles, or the clay soils, or the soils which are the behavior is exclusively controlled by the clay particles, consists of such small particles. Okay, these interact with the water, and you can see this interaction with water molecules. So we just developed many procedures new procedures in simulations, molecular level simulations, and then we use these single particles and saw different kind of behaviors, like cation hydration of the surfaces of the clay particles, and finally we try to create the realistic loose fabric of the soil and 3D compacted fabric of soil. You can see here, this is one of the fabric which was automatically created in the software, and this type of fabric that is created in the software, and this is another type of fabric created in the software. And so these fabrics, we ran several things on it, like swelling and under different type of confining pressures, different temperatures, and different cation exchange capacities, different type of clay particles, different densities, different initial moisture contents, different initial densities, different final densities, different type of cementation materials like calcium carbonate, calcium sulfate, hydrate like gypsum, calcite, calcium chloride, and so many other variations we did on this one. And this is another form of fabric. And finally, we came up with the like model after swelling, before swelling, how much swelling has occurred. So the volume change. Initially, we just went for the volume change capacity. And the state parameter which we determined from this study was cohesive energy density. And this cohesive energy density is directly related with the basic properties of any clay structure. Any clay structure means the type of clay mineral, the distribution of these clay particles, the cementation if present, initial moisture content, initial density. So you just measure these basic parameters of the soil structure and plug into the constitutive relations which we developed. And there will be a cohesive energy density parameter that comes out of it. And this CED has relationship with all other properties like the volume change, the stress strain behavior, etc. This is what I'm going to show you. The two components of CED like electrostatic and van der Waals we determined. So this is how a realistic or universal type of modeling can be done. So this is the 2D surfaces of one part, just one part of the model. You can see two bounded surfaces, total cohesive energy density and versus the initial density. So you can directly use this one for your model. And in 3D, this is the constitutive surface. So we don't have to worry about the constitutive surfaces here. We have to just plug in the basic parameters over here. And once we do it, you can see here, we did a lot of comparisons with the actual swelling test in the lab. First of all, from the lab. So these are swell from swell test in the lab. These are the, on this axis we have results. And this is swell from the nano model. And you can see here how accurate it was to predict the swelling behavior of, or the volume change behavior of the tested samples. So this was one aspect. This is another one. There was a full-scale field test performed in the, or full-scale test performed in the field. There was a structure built in the field, and we facilitated the swelling of the clay layers in the field. And this is the line you can see here. This one, this was the swelling behavior line in the field, and this is the one which we predicted from the model. So you can see how close this model could predict even the field behavior. So this is the versatility of a universal model, that you can predict any kind of behavior just plugging in the basic parameters. Now look at the confining effect. You can see the constitutive surfaces created by this model at a confining pressure of 1000 kPa and a confining pressure of 7500 kPa. And this is very much used for the oil exploration, or we call it shale gas or shale oil exploration, where we have shale present over there. So we use this model to predict the swelling behavior of the shale present at several kilometers depth at a very high confining pressure, say 7500 kPa. And it very, very closely predicted the behavior of those samples. Okay. And look at here the same model, and you can see here the percentage swell and confining pressure. So from even more than 7500 up to 15,000 kPa pressure, the swell percentage was predicted using this model. Okay. Now the temperature effects. So since it is a universal model, so you can incorporate the temperature effect. You can see here the behavior at 25 degrees centigrade, and you can see here like calcite content, initial water content on this axis, and swell on this side. And you can see here the maximum combination of this initial water content and calcite content is giving a swelling of 3% at 25 degrees centigrade. But at 80 degrees centigrade, you can see here the swelling goes up to 300%. Too much swelling over there. And you know the importance of temperature is for the deep shafts in shale or clay soils. which usually are used for the nuclear storage, nuclear waste storage. So there the temperature becomes very high because of the decay of the nuclear waste. So this is how we modeled, and it also very well predicted the behavior of the in situ behavior of these of the shale present at that level and that temperature. Now the same model we have used to predict the stabilization measures. You can see here these are different bars showing shown in two different colors. You can see the blue one, basically this is swell pressure from experiments, and the orange or the brown ones are the swell pressure from model prediction. And you can see here how closely we were able to predict the swelling pressure of these samples. We just use the basic constituent knowledge, and we plugged it into the model, and it predicted like 365 kPa swell pressure, and the real behavior was 379, and so on. And this one was using lime also. Like for example, this one was 0% lime. When we use 2% lime, you can see this 203 versus 285, 5% 200 versus 228, and 8% lime 174 versus 182. And similarly, we did it for potassium phosphate, and you can see here again a very close comparison of experimental results with the model prediction. Okay, and here potassium chloride, you can see again the prediction by the swell pressure prediction by our nano level constitutive model. Okay, we also used this is just a comparison now of different stabilizers together. So this gives us a very good idea of this one. Even we use this model to predict the type of fabric or structure in the soil. Okay, so if a combination of CED, which I mentioned to you as a state parameter, and the density is falling in this zone, we can say we have a dispersion zone. Okay, if it is in this zone, we call it flocculated zone. If it is present in this zone, the fabric or the structure of the soil would be more or less very close to the agglomeration zone. Okay, this way. And finally, in addition to the swell model, this is how we develop the shear modulus or the modulus versus CED at different strain levels. So if we combine these stress strain, this stress strain model with the volume change model, this gives us a complete behavior model for the swelling clays or swelling soils. I will say swelling soils because whenever clay is present in some substantial quantities, even sometimes 20, 30, 40%, even sometimes 10%, can control the behavior of the soil absolutely, because they are just covering the sand particles because of the very high surface area. So the behavior is exclusively controlled. Even the shear behavior or stress strain behavior or volume change behavior is exclusively controlled by this model by clay, and we can use this model. So this is the regime of soils that I'm saying that can be modeled using our nano model. But in case of pure granular soils like sandy soils or gravels, I mean, as Dr. Mubashir very rightly pointed out, that it's difficult to consider as a continuum. Maybe we should go for particulate type of analysis, and there are software available, and there are routines available that can help you in finding out a universal set of parameters for the sand or gravel models. Okay, so that's all from me. But last message I want to give you before I conclude. I'm sorry, I think I took maybe a few minutes more than the scheduled one. I just want to highlight the importance. I think I expressed it during the lecture, but just to summarize it, that geotechnical field or geotechnical specialization has a special relationship with all other disciplines in civil engineering. Like for structure, transportation, and water resources, we are the one, we are providing supplementary information. We are not independent workers. So always we provide information for the design of structures, for design of transportation infrastructure, and for the design of water resources. So they are dependent on us. So it is very important that we emphasize to them that in order to in order to get a most economical design, structural engineers or other specialized civil engineers should have a close relationship with the geotechnical engineering through soil structure interaction or constitutive modeling. Till the time this is not present, we cannot have any economical design. If geotechnical engineers are far over here and they are doing some empirical analysis, and structural engineers are here and they are considering soil as perfectly elastic material, they don't know the importance of the constitutive modeling, they will never ever come closer to us to do the real soil structure interaction. And this is only possible if we know the real constitutive model, if we do have a real knowledge of the constitutive modeling. Okay, the most economical civil engineering design is possible only through this interaction. So this is my final message, and that's why I called initially a very, very important topic in geotechnical engineering, and at least understood and maybe least valued in geotechnical engineering. And I really appreciate Dr. Mubashir that he, considering the importance of this topic, and he invited me to present whatever I have on this topic. And at the end, if you people have any questions.
Thank you very much, Jazakumullah Khair, Dr. Habib-ur-Rehman. This was really one of the, I would say, most wonderful lectures I've ever listened. I've really, as far as I am concerned personally, I've learned a lot of things. I would say I was able to link a lot of dispersed knowledge into simple, beautiful connections to understand this complex topic in geotechnical engineering. I'm really grateful, Dr. Habib. Before we take some questions from the students, if they have any, I would like to make one note over here that in your nano or micro level modeling, like you already said that it's more applicable to plate-like particles or nanoparticles like clays and so on. What do you think? What is the avenue in this innovative approach to be applicable to granular materials? Because we already know that the granular materials, the behavior is not independent of their particle shape and size. That has to be considered in all the models. So how would you think that this innovative model of yours can be extended to granular materials in future, so that we can get a research idea for it actually for our students and so on?
Yeah, actually that's very, I think you can say a question that will open real doors for new research, and that should open the doors or new horizons for new research. Of course, that's why I limited my model to the soils where either exclusively consisting exclusively of clay particles, or where the behavior is exclusively controlled by the clays. But as you said, that for granular materials like maybe non-cohesive silts, sands, and even gravels, we need to have this kind of model. Now the limitation of molecular level modeling is that we cannot model sand particles, because sand particle is too big to be accommodated in any molecular. Even the supercomputers I have used, I just wanted to mention, I use supercomputers to run these simulations, high performance computers to run these simulations. But for sand, to simulate the sand and gravel particles under molecular simulation regime, no, it's not possible. So that's why I mentioned, and you also mentioned, that it should be based on discrete element modeling. We call it particulate mechanics, based on the particulate mechanics principles. So there are softwares available that can simulate different shapes and sizes and configuration of the particles, and different surface characteristics of the particles, like sand surfaces, different type of sand surfaces, different type of silt surfaces, different type of gravel surfaces, shapes, round, the elongation, and other dimensional inputs. So those softwares, some of my students, they worked little bit on it. They use this discrete element modeling for the simulation of angle of repose for sand particles, and they published some stuff on that one. I think that is the direction. That is the direction, and I really, I mean, appreciate that you raised this question. I have always in my mind also that sometimes we should develop a parallel model for the non-cohesive soils or particulate soils, I will say. So the need is to go for these softwares, look at the capabilities of these softwares and what type of softwares that can easily model the basic parameters of the sand particles, silt particles, like surface friction, their angularity, etc., etc. So the software which very closely can do it, I think we can choose it and we can start doing work on that one.
That's wonderful. One more comment, sir, that because this was like you have already said it, that the constitutive modeling itself is a graduate course itself. We cannot cover it in like 1 hour or 2 hour discussions, but wonderfully you have covered all the basic concepts, and I hope they are very beneficial to the students. Along with that, I would request that if you have some kind of research papers or references which you have used for preparing this wonderful lecture, if you will be happy to share with us, we'll be grateful.
Sure, inshallah.
Yeah. Lastly, I would request all the students, if they have any questions, please you can ask. Otherwise, we can conclude today's webinar. Yeah, over to the students, please, if you have any questions. Students are always good listeners.
So either they understood everything or they didn't understand anything.
Okay. If they haven't any question, I'm sure they're at least listening. I would, before we leave this webinar, I would request Dr. Habib to say a few words of or as a piece of advice to our young geotechnical engineers, other than constitutive modeling.
Okay. Geotechnical engineering, in my viewpoint, it's a more of an art than science.
Mm-hmm.
It's a very I think once I think I was reading a textbook and the author wrote that we should develop feel for the soils, and this is very important message for the geotechnical engineers. I mean, you can have knowledge of all kind of closed form solutions. You can have knowledge of all kind of highly advanced constitutive models. You can have all kind of complex tools for the analysis. But till the time you have the real feel or you can say conceptual model in your minds of the behavior of clay, behavior of sand, behavior of gravels and rocks. Even rocks, you cannot model anything. You will definitely end up in wrong models. So try to develop a feel of the soil, and the feel of the soil can only be developed till the time, time you start having the soil in your hands. Okay, yes. Take the soil in your hand. Look at the behavior during triaxial test. Look at the behavior when doing field testing. So this will give you definitely a model in your mind. Yes. And if your model does not synchronize with what you are producing, then you will be alarmed. Yeah. You'll say, no, it is soft clay and it is giving me such results which are not making any sense, and something like that. So the most important thing is you have to love the soils and rocks. You have to go and watch them, and you have to incorporate their feel in your minds. Only then you will be an excellent geotechnical engineer.
Wonderful piece of advice, Dr. Habib, with the wonderful lecture today. And I'm again really very grateful to you that you spared time from your busy schedule, and you shared very knowledgeable lecture slides and materials on this innovative and I would say advanced topic in geotechnical engineering. Again, thank you very much, Dr. Habib. Jazakallah khair, and thank you to all the students for sparing the time for this webinar, and I think we can conclude now. So I would say again, thank you again to Dr. Habib. So,
okay, thank you, Dr. Mubashir.
Thank you so much.
Calling me. Okay.
Jazakallah khair. Assalamu alaikum wa rahmatullahi wa barakatuh.
Walaikum assalam.